Hi everyone and welcome to the second Advanced Higher Chemistry video. We're still focusing on some Unit 1 today, but today we're going to have a look at something called spectroscopy. More specifically, we're going to have a look at atomic emission and atomic absorption spectroscopy and why they come about and how we can identify elements because of this. Now, the word spectroscopy, it's the study of light and how it interacts with matter. Now, we use atomic emission and atomic absorption spectroscopy in order to identify lots of different samples and in quite a few other different applications that we won't really go into just now. But we tend to use it to identify, so qualitatively identify something, or we can also use it in a quantitative manner. And what quantitative means is we can generate numbers and data from that and get an idea maybe of how much of a sample is present. So it gives us spectra that we can analyse. It gives us not graphs but pictures essentially that we can have a look at, that we can compare to known samples for us to be able to identify things from unknowns. This relates back to flame testing a little bit from our National 5 course that you'll have had a look at previously. And it's based on this idea in that we look at a continuous spectrum. So when light passes through a prism, if you have white light, it goes through a prism, and what you see on the other end, you may have done this in broad general education in second year or first year, you tend to see all the colours that light is made up of. And so we tend to have our prism, which I'll show you here, just as a triangle. This will be on another slide, but I quite like drawing these kind of things out. So we would have our prism, we would have our light source here. So say I've got some kind of a light bulb. My drawing skills are terrible, by the way, so I apologise already. So here's my light source. And if I've got white light, that white light comes into the prism. And what will happen is, firstly, it will change in its direction as it comes through and hits both sides of the prism. But what we see coming out of this side, and I'll just draw it like this, are multiple colours. So let's just say that we're going from red, orange, yellow, green, blue, indigo and violet. All the colours essentially of the rainbow that white light is made up of. And this is probably, you can see on the slide that you get this continuous spectrum. It's not just one shade of red and one shade of orange. It goes through from red all the way through to the other end to violet. This occurs when anything emits light. We can look at the light it emits, we can pass it through some kind of a prism, and we can see what that light is actually made up of, because what we see would be a combination of these different wavelengths. If you remember from, if you've done physics or from the previous lesson, all these different colours of light have different wavelengths. This one beam of light contains all of the wavelengths of these colours, and we were talking about the visible region just now. You can have wavelengths that are out with that, we just can't see them. But if we had any source of light, pass it through a prism, we could have a look and see which of these wavelengths is there and what it's actually emitting, and that will give us some kind of a fingerprint. But what we see just now is this continuous spectrum, so we're just going straight through from red all the way through to violet, with all of the colours in between. And this was used quite well, and you can see on the slide there, as an album cover for Pink Floyd for Dark Side of the Moon. And you can clearly see there's white light coming in one side of the prism, and the other side we're seeing this rainbow out the other side. So that's where this kind of been seen in more kind of popular culture rather than just an advanced higher chemistry lesson. So atomic emission is spectra. What is it? What we need to do first is we need to take our sample, and we tend to change it into a gas. We like doing things with samples that are in a gaseous state. Remember, when we speak about ionization energy, we're always talking about removing electrons in the gaseous state. But what we tend to do in this technique is that we take a sample, we change it into a gas, and then we use some form of energy to excite the electrons in the atom. Now, what do I mean by that? So just now, our understanding of an electron, or as where the electron is, we have our nucleus, so I'll just put N for nucleus. We then have our outer shells, or sorry, our electron shells. So I tend to fill them like this, and we have these electrons, and you might have more on the outside. this is how we teach you how these behave. You're going to learn later on, not today, but you're going to learn how these exist. This is just showing us and giving us an idea that you have these different energy levels. Let's have a think of this in a more linear sense just now. So let's take these different shells and essentially represent them as lines. So if I had an electron, let's just mark it as an X here, and it's in a shell, okay? It's in a shell out with the nucleus. There are other shells, other energy levels that electron is not in. And what we were saying is if I put light into my samples, this whole thing's my sample, this electron could jump up. It might jump up here, it might jump up to a different energy level. That's what we are meaning by exciting an electron. We're taking the electron, we're giving it energy, that electron is jumping up to another energy level. What happens next? So this is like my before. And this part is like my after. Say my electron has come up here. Okay. It drops back down. It's only been excited for a short period of time. We've taken an energy. It drops back down, and when it drops back down, it emits energy. And that energy is in the form of a photon of light. So we're exciting the electron. And here, the electron falls back down. As it falls back down, it emits a photon of light, and that we can see. The photons of light, as this drops back down, is what we can see and analyse if we pass it through a prism and see what the wavelengths of light it emits are. And that tells us an awful lot about what we have in our sample. So if we have a look back at the slides just now, it says the patterns of the lines in the spectrum are characteristic for each individual sample. These lines represent our different energy levels. They could be in a different sample, closer together or further apart. So maybe same bottom, but I'm up here for my other ones. Okay, so if I had an electron here, it needs more energy to actually be promoted up to this one. And therefore, when it jumps back down, it releases a photon of greater energy. This is the concept that we're trying to have a look at just now. Now, this is my sketchings. I'll show you some other real diagrams in a second, but I like to sketch as I speak. The patterns of the lines on the spectrum are characteristic for each individual sample. So if we have a look at the slides again, the example I've got on here is sodium chloride sample in a flame. So this is kind of like your flame testing that you did in National 5. When we saw that, we saw an orange colour in the flame. And that is because we've taken a sodium chloride sample. Now, ideally for atomic emission spectrum, that would be a gaseous sample of sodium chloride. But we put that, we burn that in a flame, and the heat energy is making those electrons jump. They then fall back down, and that emits a photon, and emits photons that allow us to see the orange colour of the flame. That is then passed through a prism, you can see in the middle here, and as you go we get this line emission spectrum, which looks something like this. This is a little bit zoomed in, but this is the emission spectrum for helium. And what we see is when that passes through the prism, what we see are distinct bands, so lines. So we get this dark background because we're not seeing any of these wavelengths, but we see light of a wavelength of 668 nanometers, another one at 588, 502, 492, 471, 447 and 402. These are all wavelengths of light that have been emitted by the helium atom. Each of these corresponds to one particular jump, which I'll show you in a wee second. So anytime we see an emission spectrum, you're going to see a black background and you're going to see the coloured lines on that spectrum. And those coloured lines are for each of those electron transitions, all those photons that are being emitted. If we have a look at it here again, now I'm seeing it just not in a quite linear aspect, but here is our nucleus here. This is for hydrogen this time. Hydrogen has 1 electron, and what we're seeing is hydrogen's first electron should be on the first shell. But in this case, it's been excited, so it's already taken in energy to be excited out to this outer shell. And this line at 656 nanometers is because this electron has jumped from here to this shell. Having a look here, again, if we were in our ground state, so our non-excited state, hydrogen's electron would be on this first shell, but it's not, it's out here, it's been excited by heat or electricity, but now we're dropping back down, and we're dropping back down to the same shell, if you have a look here, same shell, but we're dropping back down from 2 shells away. And the wavelength corresponding to that photon that's been emitted is 486 nanometers. If we have a look at this one here, again, we're dropping back down to the same shell of electrons, but it's been excited further away from the nucleus. So it's got a greater distance to come down, and that gap corresponds to a photon with a wavelength of 434 nanometers. So these are distinct jumps. The distances between the shells is very specific for hydrogen, and the distance between the shells, the size of the gap between the shells, determines the wavelength of the photons that are emitted. And so we get this spectra, and this is almost like a fingerprint for hydrogen. It has these 3 specific bands at these 3 specific wavelengths. And so if we had an unknown sample and we performed atomic emission spectroscopy on it, it would produce the same thing if it were hydrogen, so we can compare it. If these bands were not there, then we could safely say that this substance was not hydrogen. If it looked exactly like this and it was the same wavelengths, we would say that it was hydrogen. Okay, so just showing you there in words, electron falling from the 3rd energy to 2nd, from the 5th to the 2nd, and from the 4th to the 2nd. So coming from other energy shells going to the 2nd shell of electrons, and that's quite important. So there are so many different possible transitions, and they can go between these excited states and lower energy levels. And you can see it there on the slide, but I will show you this as long as you can see it on the camera. We've got these energy levels. So if we start down here at the first energy level from the nucleus, so imagine the nucleus is down here. Here's the first shell of electrons, the 2nd, and so on. If my excited electron drops back down to the first shell of electron, it's going to emit ultraviolet radiation. And we see this in something called the Lyman series. So we name these series after different scientists, but you don't need to know anything about that at the moment, but we just need to know about these different series. We have the Lyman series, where you have ultraviolet light, and that is where the electron jumps back down to the first shell of electrons. The ones we just saw on the slide all drop back down to the 2nd energy level. Now, if they drop back down to the 2nd energy level, this is where we see the colours. This is where we see visible light, and we could actually see it. So if I'm dropping back down from 3rd to 2nd, 4th to 2nd, 5th to 2nd, all dropping back down to the 2nd, this is the Balmer series, and it will be visible light that is emitted. If these drop down to the 3rd shell, then what we're having a look at here is we're having a look at infrared radiation being emitted, and this is the Paschen series, and this is going from like 4th down to 3rd, 5th to 3rd, and so on. They're going down to the 3rd shell of electrons. And so we might be having transitions that are going down to n equals 1 or to n equals 3, but we visibly are not going to be able to see this. And so it's not going to have an effect on the colour for us and what we see. If they drop back down to n equals 2, then the light that we're going to see is going to be light we see that we can visibly see, and colours that we can understand and see with our own eyes, which is why we know that potassium has a lilac flame, sodium has an orange flame, lithium has a red flame, and so on, because these are all corresponding to we were heating them up, they were getting excited, and they were dropping back down to the 2nd. There may have been ones coming down to 1, there may have been ones coming down to 3, but the ones that are coming down to the second energy level are responsible for the colour that we are seeing in there. So remembering the Lyman, the Balmer and the Paschen series is quite important, just to understand that one's ultraviolet, one is visible and one is infrared. Now, atomic absorption spectrum is ever so slightly different, because in this case we are not talking about the emission anymore. In this case we're wanting to have an idea of what type of light or what wavelengths of light are samples actually absorbing. Because if they're absorbing that radiation, then it's because something's happening within that sample. So if we have a look at the slide again, in atomic absorption spectrum, electrons are promoted to higher energy levels by absorbing energy. Now I've shown you that already. We have our ground state where our electrons are sitting in an energy level. You apply heat, you apply electricity, and that's going to jump up to another energy level. The wavelength of that absorbed light corresponds to that specific jump. That specific jump requires it's quantized, it's a specific amount of energy that it needs, and only a particular wavelength of light could give that energy. And so it will absorb that wavelength of light. So if you think, again, having a look at the kind of prism idea, looking here, if you think, oh, this is a really dodgy triangle. My diagrams are infamously bad, so I do apologise. If you think that this light, and say my sample is here, I'm going to have light going into my sample. That light is going to pass through my sample, but my sample is going to absorb some of it. And if I go through here and think about what's actually going to be seen, if it was white light to begin with, I would be expected red, orange, yellow, green, blue, indigo and violet. But you'll see I've not written green here. G is missing because this particular sample is absorbing the wavelengths of light that correspond to green light. And so if I was then looking at that on a spectra, I'm going to see that continuous spectrum of light. If this was white, I'm going to see continuous spectrum of light, but it's not going to have green. There's going to be a blank space where there should be that green light that we're seeing on the spectra, and that is because this has absorbed those wavelengths of light. And so this is almost the negative of the emission spectra. We would be expecting to see a colourful background with black bands on it for the wavelengths of light that are missing. Okay, it won't be all of the wavelengths of green, I'm just using this as a very basic example, but you will have bands at different points corresponding to the wavelengths that have been absorbed and therefore taken out of the light, essentially. So we won't be able to see them when it passes through that prism. Having a look at an example of that on the next slide, it says transmitted light, so light that emerges from the sample, has some wavelengths missing due to the absorption by the element. So here is my coloured background. So there's my purple through to red. And here, these black bands are where I'm missing wavelengths. Each of these wavelengths is specific to one electron difference between electron energy levels, So the jump between, say, 5 to 2 and 4 to 2 for that specific element will be 2 of these. It'll be different for different elements. And so again, I can get a fingerprint of the absorption spectra and see this spectrum and be able to identify my sample. And like we say already, energy has been moved this time. Instead of us seeing it jumping back down, this is us having a look at promoting that electron in the first place. The convergence limit, we have the lines in this emission spectrum. Think about these as being further and further away from the nucleus. So think of the nucleus as being out here somewhere. Here is the third energy level, the fourth, the fifth, and so on. They get closer and closer and closer and closer together as you get to the edge of the atom. And this is what we call the convergence limit. So as our energy levels start to converge on each other, so the difference between them, if I was having jumps in between these, they would be like minimal energy difference between them. because they're so close together at the edge. So that would be a small amount of energy that's actually being released there, and that would be more towards our red, further out from our red and our infrared side of the spectrum. If an electron has been promoted out to this convergence limit, if I have an electron out at this convergence limit, the energy for it to drop back down into its ground state, so where that electron came from, is the ionization energy, is the same energy that's required to completely remove that electron from that atom, because it's right on the edge. So any more than that, the tiniest bit of energy more, then that's going to be gone. So this is what we call our ionization energy. It is when we are looking at the energy produced when we go from the convergence limit back down to the ground state. So to give you an example of calculations that you might need to do with this, just now I've got the atomic emission spectrum of hydrogen in here, and you'll see diagrams. Obviously we're talking about these being different colours of bands on a black background, but that's not really something that we can see in notes. But you'd have all your different wavelengths, and knowing the relationship from last time, E equals LHC over lambda, says calculate the energy of the red line in the spectrum. Now the red line in the spectrum, I'm thinking that red is at my longer wavelength, so I'm going to be looking at having the larger number here. Okay, so the smaller the number, the shorter the wavelength, the higher the frequency, the more energy in that light, and I'm looking at the violet end of the visible region. Here, this is going to be the red light in my spectrum. So if I'm doing E equals LHC over lambda, I'll be doing E equals 6.02 times 10 to the 23 times 6.63 times 10 to the minus 34 times 3 times 10 to the 8, and all of that is going to be under 656.3 times 10 to the minus 9, because remember these are nanometers. Now, since I'm using my phone to record and it is my calculator, I can leave you to work this out. Make sure when you put this into your calculator, however, that we have kind of brackets over here and this, and we're not doing anything funky with the numbers. But this is what I will be looking for you to work out the energy associated with any line of an emission or an absorption spectra. If we know the wavelength, we can work out the energy of the either just the photon itself without L, or of 1 mole of those photons, which is more common. That's what we would be looking at. There are other kinds of questions that we could have a look at as well, having a look at different ionization energies, for instance. So I have a question that says, calculate the ionization energy for hydrogen if the Lyman series converges at 91.2 nanometers. So that's a lot of information. Let's write it down. Calculate the ionization energy. Shown energy for hydrogen if the Lyman series converges at 91.2 nanometers. Lots of information. Now, we just spoke about convergence point, and that's what this is talking about here. So we are saying that the convergence point gives us this wavelength. So if we go from our convergence point back down to our ground state, then the light emitted or the radiation emitted has a wavelength of 91.2 nanometers. And it's also saying about the ionization energy. The definition of ionization energy you should know from higher, and the definition of that is the energy required to remove 1 mole of electrons from 1 mole of atoms in its gaseous state. 1 mole is the key in here. We need to be using Avogadro. So what I'm looking for again is E equals LHC over lambda. 6.02 times 10 to the 23 times 6.63 times 10 to the minus 34, and that's times 3 times 10 to the 8. All of that over 91.2 times 10 to the minus 9. I know that's kind of messy scientific notation I'm using, but I tend to do it this way. That just reminds me nanometers is times 10 to the minus 9. You can have that as long as it's correct scientific notation. There might be multiple ways that you do that, and that will give you your answer. Again, I'm not going to plug those numbers in for you just now. You can double check this though. Lyman series, we just spoke, we said we had the Lyman, the Balmer and the Paschen series. So the Lyman series is going to give us something that has a wavelength that is in the ultraviolet region. The ultraviolet region, I am looking for a higher amount of energy than if I had an infrared. These are things that you can be thinking about and checking as you are going on through this. So this is how we would deal with our ionisation energy. It's quite important just to realise that you're talking about 1 mole. It might say calculate the energy of 1 photon, and in that case we're not going to use L. It's going to be E equals hc over lambda. And that's the kind of thing that you could look at. Another thing that might come up is if you remember looking at spectroscopy and higher, you would get questions, and I guess they look kind of similar to this. So this question here has hydrogen, helium, lithium. It has basically the absorption spectrum for multiple different elements. And then what it does is it shows you on the other side a spectrum for an unknown, and samples A and B for this other question as well of things, and it's basically getting you to compare these and saying, right, hydrogen has these bands, do those bands appear in my unknown? Yes or no? Does helium appear in my unknown? So you're double checking and trying to rule out and work out which of these lines comes from which element. Some of them are there and some of them aren't. So that's the kind of thing that you could be asked with this.